Yeah, you must start.
Yes. So very good evening to all. So last class I did not mention the telephone number and email ID. So now it is mentioned in one of the slides. You may kindly note. At any time you can call me or you can mail me also. So please feel free to contact. So last class we were discussing about solid state NMR, solution NMR, then what are the different interactions which are operating in solid state NMR. So this we have discussed and compared with that of solution NMR. So previously, as I mentioned, people were thinking that solid state NMR used to give very broad line shape and then it's not possible to interpret. But now theoretical understanding has been made such a way that we can interpret the solid state NMR line shapes and we can get meaningful information regarding bond length, bond angles, in fact, the structure of solids from such solid state NMR patterns. So towards the end, I think we discussed about the different NMR interactions. Huh? Yeah. And we discussed the different NMR interaction which you might have already studied. I discussed about gamma values, which is nothing but the gyromagnetic ratio, very important parameter, gyromagnetic ratio, which we will discuss because that is a parameter which decides the extent of dipole-dipole interaction. If dipole-dipole interaction is strong, means you will have very high value of gamma. That is why protons are having very high dipole-dipole interactions. Particularly if you record NMR spectra of proton NMR spectra in solids, you see extremely broad line shape, which are difficult to interpret. But if you compare that in solution we get proton NMR spectra gives almost everything. You can get very easily get the information and you can arrive at the structure of the molecule. But in solids, it gives a very broad line shape, making it difficult to interpret. So these are the two slides which we have discussed towards the end, which I have mentioned about this gamma value, which is nothing but the gyromagnetic ratio, the nuclear G factor. These things were already taught to you in the beginning, so I am not going to cover. But just for the sake of completion, I am mentioning this mu is equal to gamma p. So gamma p is nothing but the nuclear gyromagnetic ratio and p is the angular momentum. So if you measure the magnetic moment of the nucleus and if you know the magnetic angular momentum, you can calculate the gyromagnetic ratios. There are nuclear physics experiments people do to find out the gyromagnetic ratio of different nucleus. So all those things were covered or discussed in the last class. Now let us go to this second lecture. The second lecture today, we mainly discussed about, sorry, I think again the proportionality sign has not come. So we mainly discuss about the interactions. So there is something you can see the first dipole-dipole coupling. You see I1 and I2. I1 is one nucleus, I2 is another nucleus. So there is a distance, there is a double arrow that is called the bond vector. So this bond vector make an angle theta with the applied magnetic field. That is called a dipole-dipole coupling. So in a powder sample, if you see, you have all sorts of orientation. If you take a single crystal, of course, we have different orientations. But the moment you go to powder samples, because powder samples, we have a random distribution of grains, crystals, etc. So you see the bond vector must be randomly oriented. It will not be at an angle theta with respect to a particular angle theta with respect to the applied magnetic field P. It will be randomly oriented. So then what happens to the dipolar interaction when it is randomly oriented? Even single crystal also, it is not necessarily that the bond vector which is represented by I1, I2 must be aligned at an angle theta with respect to the magnetic field. There can be different orientations depending upon how you keep, depending upon the orientation in which the crystal is grown, etc. So dipole-dipole interaction, as I mentioned also in the last class, this is one of the major interaction. I am sorry that that question mark is still there. It is a proportionality. And later I will do actually. I think somehow, I think version to version changes are there or I could not convert it. So another interaction is nothing but the quadrupole interaction, which is quite dominant, quite popular in solid state NMR. As I mentioned, I think 60 to 65% of the nuclei in the periodic table have nuclear spin greater than half. So once the nuclear spin is greater than half, there is a charge distribution is asymmetric, and this leads to quadrupole moment, and you will get prolate. You might have heard about prolate and oblate type of thing. So that type of electronic distribution, and this will give to some sort of a broadening as well as a coupling constant, etc. And the third important interaction is chemical shift anisotropy. Why we call about chemical shift anisotropy? Because the electron distribution around a nucleus will not be symmetric, even if it is a spin half nucleus. For example, if you take phosphorus, depending upon the coordination environment, phosphorus can have 3 coordinated, 5 coordinated, and higher coordination values. So depending upon the coordination number, the electronic distribution changes, because you have different oxygen atoms may be there. Sometimes the oxygen may be linked to some other carbon or some other phosphorus or some other metal. Then accordingly, the distribution in the electron density around oxygen changes. So once the oxygen changes, that will have an influence on phosphorus. So as a result of this, there in solid always this anisotropy exists. That is we call as the chemical shift anisotropy. These are the 3 important interactions we study in this solid state NMR. So before continuing further, there is one beautiful book written by McKenzie on this type of interactions existing in solids, which is available in our library, also must be available in many libraries. That is edited by, I think, Bergaman Press, material series. So this first 100 pages gives first 100 pages discusses about the interactions, this type of interactions in detail. Of course, we will not go in details. So what I am planning to do is that first maybe 2-3 classes or 3-4 classes, all the physical aspects of solid state NMR will be described, and then probably 6th and 7th or 5th, 6th, 7th, 8th we will go for some examples. And then 1 or 2 problems we will solve how we can use solid state NMR to predict the cation distribution. So this is what we have planned, and towards the end, maybe 8, 9, 10 or 11, 12 classes, we discuss about multi-dimensional NMR and then cross-polarization techniques and multiple sequence, etc. So let us go further. Okay. As I mentioned, in a solution, what happened? The interactions are isotropic. Everybody must be knowing. If you take a nucleus, this I have also mentioned in the last class. All interactions should be isotropic. It will be like a spherical in nature, so they get averaged out. But in solids, situation is not like this. In solids, see, we have different types of solid: cubic system, tetragonal system, orthorhombic system, monoclinic system, triclinic system, etc. Wherein each atom is surrounding by different ions, or in each ion is surrounded by different ions, but not in a symmetric fashion. There is bond length differences are there, bond angle differences are there. So a lot of differences are there, and they are not going to get averaged out. So if you measure, for example, chemical shift or the electron density in one direction, where let us say it is in the x direction, it will be different in the y direction, and it will be also different in the z direction. This is not the situation with molecules like ethyl alcohol or acetone, etc. Because everywhere, suppose you probe carbon or proton, the symmetric charge distribution is symmetric. But in the case of solid, along the x-axis you will have a different electron density, y-axis you will have different density. So this will create some sort of an asymmetry, or better word is anisotropy. So anisotropy exists in the case of solids, particularly with respect to the electron distribution. Not only electron distribution gives to the chemical shift or the shielding, so that is anisotropic. In addition to that, the interactions like dipole or quadrupole interaction, etc., they are also anisotropic in nature. So any physical phenomena which is anisotropic in nature is explained with the help of a tensor. So there are vectors are there. Actually, tensor is nothing but a vector of a vector. So either you can such type of anisotropic interactions, anisotropic in x, y, and z direction can be expressed with the help of a tensor. So here we simplify, we only work on second rank tensor, because first rank tensor is nothing but a vector. And the zero rank tensor is nothing but a scalar. So zero rank is nothing but a scalar, first rank is nothing but a vector, and the second rank is nothing but a real tensor. So I will just give you one or two slides regarding tensor. Probably this we will discuss also maybe towards the end of the this course. So tensor is nothing but a vector, is related to vector. So normally vector, what we write, for example, I have shown here, capital S is a vector, is equal to K into small s. Small s is a vector. So small s and capital S are vectors, and K is a constant, is a number. We can say is a nothing but a scalar. It's just a number we can say. So, and also we can see that yes, capital S and small s has same direction. But if you consider electron density or dipole-dipole interaction or quadrupole interaction, we cannot write like this. We cannot correlate with respect to a constant because their directions are different actually. Not the same in all the direction. So K need to be a tensor actually. Then only we will be able to define that actually. So again, I am discussing about tensor only. Scalar we all know. Scalar means only magnitude is a number. Like I told, K is a number. So only magnitude, no direction, 1, 2, 3, etc. So scalar is nothing but with tensor with rank 0. So the moment you say vector, the vector has magnitude also direction. Just now I have mentioned. So if direction is a particular arrow, it will show, and the magnitude is some value. For example, I have given a vector here. T is equal to ax plus by plus ez. Xy is a show some sort of a directions in the xy z direction, and abc can be some scalar. So here you can say three components are there in each along the x, y, and z axis. You can see here that is a vector. But the moment you go to tensor, what happens? A component in the x direction is also will have a component. The same x component will have an y component, and the same a component in the x direction will have a corresponding component in the z direction. So we have xx, xy, and the xz. Similarly, y component also will have, it will not confine to y solely to y axis. It will confine to x axis also. It will confine to z axis also. So we have y, x, yx, and yz. Similarly, anything along the z axis, not only confine along the z axis, it will confine along the z axis, zz, zx, and zy. So in that way, you generate three components. So if you take a tensor, for example, if a tensor of rank 1, then 3 raised to n component, which is nothing but 3 raised to 1, which is nothing but 3 components, as I mentioned in the case of vector t. There are only 3 components are there. But if the x component is also having a contribution to the y axis and also having an z, then n become 2, so we will get 9 components. So that is called a tensor with rank 2. So we can see that the components can be expressed with the help of a matrix. You see, we have x component is also having a component along x axis also, y axis also, z axis also. So that is why xx, xy, and xz. Similarly, the y component is also having a component in the x axis, y axis, as well as z axis. So we have, that is why 2 vectors are coming. Y axis is having a component along x axis, y axis, as well as z axis. Similarly, the z component is also having a component along the x axis, y axis, and z axis. So we have total 9 components. So that is why the rank of this tensor is 2. Rank is normally number of components is expressed by the number 3 raised to n, where n is nothing but the rank. So n is equal to 0 means we have only 1. N is equal to 1 means we have only vector, and n is equal to 2 means we have 9, which is a second rank tensor. We have also a third rank tensor, but in all NMR studies, we are only bothered about the second rank tensor. If you go to a third rank tensor, the matrix number will be increasing because here 9 components are there, it will come at 27. Because 3 raised to 3, which is nothing but 3 into 3 into 3, which is become 27. So matrix will be bigger. So instead of sigma xx, we have sigma xxx, sigma xxy, then sigma xxz, then it will continue like that. So like that, 3 components will come here. So fortunately, we have only all the NMR interactions can be represented by a second rank tensor. So I have mentioned in each direction, x, y, and z physical properties expressed as the sum or function of the three components. So total we have 9 components. So dipole-dipole interaction also can be expressed like this. Chemical shift also can be expressed like this. Quadrupole interaction also can be expressed like this tensor. So sometimes people, so two components are there now, 1, 1, 1, 2, etc. So people also call as a diode. So diode terminology comes from polymer actually. Sometimes two different polymers people call as a diode. So that is why this component comes from this terminology comes from the polymer terminology. So Tij is a general terminology to represent a second rank tensor, which is the 9 components. So as I mentioned, all NMR interactions can be represented as a second rank tensor. Similarly, we have got Tij also, where there we have 27 components. We will not be discussed that. In addition to NMR parameters, many materials properties like electric susceptibility, dielectric constant, thermal conductivity, stress, strain, optical parameters, optical polarizability, all these can be expressed with the help of a second rank tensor. This is just for your information. So tensor, we say tensor can be converted. For simplification, sometimes people say all the 9 components is difficult to express or difficult to explain. So people sometimes for understanding and simplicity, they make a tensor into, they diagonalize the tensor. So that is what we have got, only non-zero value. Diagonal components are non-zero. Off diagonal components are 0. So the moment you do that, we call it as the tensor is in principal axis system. So principal axis system is easy to understand. Actually, there are two frames. One is principal axis and another is laboratory frame. So, and another is rotating frame. Rotating frame probably we may not discuss, or maybe towards the end we may discuss. But for the time being, we will discuss regarding the laboratory frame and the principal axis frame or principal axis system. So principal axis system is only to simplify and study the interactions. So in principal axis system, the tensor can be represented as only a 3 component. Once you have a 3 component, we can generate a parameter called isotropic value, which is nothing but 1 by 3 times sigma xx plus sigma yy plus sigma zz, which is nothing but the isotropic chemical shifting. So principal axis also I have shown here. So by you can do, there are procedures are available to do this, how to convert a diagonal full matrix into an diagonal matrix. So convert from laboratory frame to the rotating frame, all those things are possible. So that just I have given an example here. There's an alpha beta angles are involved. So the moment a PAS is converted or a principal axis system is converted to laboratory phase, it looks like this. So as I mentioned, 3 frames we consider normally. Rotating frame we will discuss it a little bit later. But the laboratory frame and the principal axis system, which we have just now mentioned, I think must be clear to you by this time now, because these are the 2 systems. In the case of a laboratory frame, we have the 9 components, whereas in the moment you convert the principal axis frame, then we have only 3 components. Normally, as I mentioned, we have 3 interactions. One is dipole-dipole interaction, another is quadrupole interaction, and the third one is chemical shift interaction. So normally we write like this. Any Hamiltonian for NMR, we can write like this. I is nothing but the spin. S is also a spin, and A is the interaction tensor. S can be I also. So it's a homonuclear interaction, otherwise it will be a heteronuclear interaction. This is the general way we write this, the interaction Hamiltonian. Forget about this, I have already discussed about tensor, so we will not go further in details. And 90 degree, 180 degree pulse, I am definitely sure that you people must be aware of that, and it was done many times in the class. Now, let us discuss in detail how a dipole-dipole interaction can affect the NMR line shapes. So I have given for a classical understanding, let us say 2 magnets are there. One magnet is given by K and another magnet is given by J. J magnet and K magnet. Once you keep a magnet, what happens? We have lines of force are there. Correct now. So magnetic flux density will be there. Then magnet will have magnetic moments, etc. So magnetic moment, qualitatively, one can say if the magnetic moment is high, means it has a very high tendency to align along the applied magnetic field. That is a measure of its tendency to align along a magnetic field. That is, of course, formulas are there which I am not going to discuss. But magnetic moment, higher the magnetic moment means it has a more tendency, it is like a more magnetic in nature, or it has a more tendency to align along the applied magnetic field. So these two magnets I and J can interact, and classical expressions are available. You can see anywhere if you put Google what is the interaction energy between two magnets, you can easily calculate as electric dipole interaction is nothing but magnetic moment of J, magnetic moment of K divided by R2 minus 3 into, this can be derived also, which we are not going to discuss. So this is the basic expression. So once you know the energy in quantum mechanics, we people know, if you know the energy term, definitely we can go for the Hamiltonian. So we can only difference in that Hamiltonian we get also the operator, also in the community picture. So this is nothing but the Cartesian picture in normal coordinates, and if you convert into polar coordinates, you will generate an expression like this for Hamiltonian. So mu 0 by 4 pi, you know, is nothing but that mu 0 is permeability of the free space, is a constant. And gamma j is nothing but gamma j, as I mentioned, gamma j is nothing but the gyromagnetic ratio. Yes, gyromagnetic ratio of the J nucleus, and gamma K is nothing but the gyromagnetic ratio of the K magnet. Magnetic, you can say for the time being as nuclei. For example, I told two magnets J and K. You now assume J is one nuclei and K is another nucleus. It can be, J can be a proton, K can be a carbon 13, or J can be a proton, K can also be a proton, or J can be a silicon, K can be an aluminium. So you can consider that way. So you come like you get an expression for Hamiltonian for dipole interaction as mu 0 by 4 pi into gamma j, gamma k, h cross square divided by r cube into a terminology called it. I am not going to the details of this derivation, etc. These equations are required to understand the angular dependence as well as to understand the line shape of powder samples. That is why I have given this expression. So mu 0, as I mentioned, it is permeability of free space. I have again already told. And h, you know, r is nothing but the bond vector, the distance bond vector, So the first term, this is called the dipolar alphabet. There are many terms are there which we will not be discussing. First two terms only, the term A and the term B, we will discuss in detail. If you see term A, term A is having a parameter 3 cos squared theta minus 1, and the term B is also having a parameter 3 cos squared theta minus 1. The remaining terms, you see, they don't have 3 cos squared theta minus 1. Their angular dependence is more complicated compared to the 3 cos squared theta minus 1. Here sin theta, cos theta, and all those things. So here also it is different. This is made in the polar coordinate expression. So these two terms, in fact, if you see that these two terms are contributing more to this HD. First two terms, A and B. C, D, and E contributes to a lesser extent. Of course, they contribute to the relaxation phenomena, but A and B contribute to the line shape. So that is why this A and B term we explain in detail. So this A and B also, these theoreticians call as secular components. Why we call it as secular components? Because it's commute with IZ. We will not go into detail. So sometimes in books they write like A and B are secular components. So that is why we take into consideration of only A and B. C, D, E are of minor importance because they are negligibly small and they are non-secular components. So forget about that. But one thing you know, the interaction 3 cos squared theta minus 1 term, the angular term is predominant in the first and second expressions only. And another term is also there, j plus, k minus, k plus, and etc. These are called rising and lowering operators. Probably you might have learned also in your other solution number. Rising, beta to alpha is rising, alpha to beta is lowering. So this type of rising and lowering operators, probably you might have studied in your previous classes also. Homonuclear, they will be contributing a mode. If, for example, you are studying the dipole interaction of two protons, then one proton can be called as alpha and another proton can be called as beta. So alpha, beta, alpha, beta, this type of rising and lowering operators become very effective at that time. But if you take a heteronucleus, like carbon 13 hydrogen. Then what happened? This rising and lowering operation is not, does not have conservation of energy. So the moment that conservation of energy is not there, the B term becomes smaller. Only at that time we only consider A term. So the dipolar interaction involving heteronucleus, we basically consider only the A term. And dipole-dipole interaction involving homonucleus, we consider both A and B nucleus. Because I am repeating once again, the B nucleus is having a rising and lowering operator. If it is a heteronuclear spin, then it will not be energy conserving this rising and lowering operation. So this contribution is less. So other contributions are negligible. They contribute to relaxation, but we will not be considering further. So A and B, as I have mentioned again, I am repeating this. A and B are the secular part of the Hamiltonian, independent of the time. Because why we call it as a secular part Hamiltonian is that commutes with the IZ operator. And C and C2F are not secular part of the Hamiltonian, and they have time dependent at frequencies omega 0 and all those things. So they are not of meager contribution. Even B term also, B term is predominant if you have a homonuclear dipolar coupling. Homonuclear means what? If you have proton and proton, one proton HA is coupling with another proton HB, then it is a B term is predominant. If it is a heteronucleus, what happens? This type of rising and lowering operators will not lead to energy conservation, and this invariably lead to reduction in their contribution. And that is why we may not be considering B at that time. But you remember that both the B and the A term have 3 cos squared theta minus 1 dependence. Just between the coupled levels, as I told, instead of alpha 1, alpha 2 are homonuclear coupled. You can say one is one proton and second is a second type of proton. So A proton and B proton. You can say alpha A, alpha B. 2 different types of proton, they are coupled. So T1 is the lower level, correct? T0 is nothing but alpha, beta, beta, alpha. That can be expressed in this type of level. And the excited state is nothing but beta 1, beta 2. So 2 transitions are only possible, that also you know. Either T1 to T0 and T1 to T0 to T minus 1. These things I think definitely that other class it might have discussed. And raising and lowering operators also it might have discussed in the class, because raising and lowering of I plus is nothing but a raising operator. Sorry, sometimes I am writing below and sometimes I am writing above. But I plus means it is a raising operator. So if you raise alpha, alpha cannot be raised actually. So I beta can be raised to alpha. So I minus can be definitely, alpha can be reduced to beta, but beta cannot be raised. This thing probably. So if you see the frequency, in the case of a homonuclear case, you will get an expression. If you solve that equation and if you based on quantum mechanics itself, this equation has been derived. So frequency is nothing but nu 0 plus or minus 3 by 4 into RDD. This is the term introduced by the dipole-dipole interaction, which is nothing but the perturbation. And this perturbation is nothing but the dipole-dipole coupling constant. So dipole-dipole coupling constant is given by this expression RJK. J is one nuclei and K is another nuclei. You can see here the RJK is a parameter which is inversely proportional to R cube, where R is what? The bond vector or the distance between the nuclei. So as the distance between the nuclei increases, the R cube will increase, and since it is in the denominator, you will keep on decreasing the lower, dipole-dipole interaction will keep on reducing. That is why, if I have in the first class, I have shown you sodium chloride structure. Sodium is having a near neighbor chlorine at a distance of A by 2. But if you increase that distance, then what happens? The dipole-dipole interaction will also decrease because R is decreasing. So in fact, if R is decreasing, it is decreasing as inverse of cube. So the moment R increases, this parameter increases, and as a result of this, you will have lower and lower dipole-dipole interaction. So that is why to manipulate dipole-dipole interaction, you have to first work with only the near neighbors. We need not bother much about the next near neighbor and next to near neighbor, because the distance parameter increases and dipole-dipole interaction decreases with the distance. So just I am giving you an example of a molecule called calcium sulfate containing water. That is called CaSO4H2O. CaSO4H2O is a very unique molecule, actually, very unique molecule, because this water molecules in that calcium sulfate is non-interacting. So only the two protons of water molecule interact because they are well separated. So inter water molecule interaction between two water molecule interaction is negligible, but within a molecule there is a considerable interaction between the protons. So this is a unique case in which calcium sulfate water is having a water molecules which are isolated water molecules are there in the lattice, and these isolated water molecules have two different protons. Each water molecules have two different protons, and they dipole couple and produce a line shape somewhat similar to this. So let us say how the line shape is coming. So when the bond vector, you can see here, when the bond vector is aligned at an angle 90 degree with respect to the applied magnetic field, that is called the theta is equal to 90 degree, we get two peaks, because you see the expression nu 0 plus or minus 1. So there will be something in the nu 0 at the center, and there is one component coming here, one component coming here. Because theta is something getting incorporated here. So we will get two peaks. That is what we are seeing here, one here and one here. The moment the angle decreases, now the angle becomes 60 degree. Then what happens? This distance between them decreases because the parameter cos theta, if you see cos 6 theta decreases and 1 minus cos theta further decreases, and then you will get the separation decreases. The moment you go to 54.74 degree, the moment you go to alpha and beta joins to give a single peak. You see here, alpha and beta, the moment you go to 54.7 degree, then theta become, cos squared theta become 1 by 3, 3 into 1 by 3 become 1, 1 minus 1 becomes 0. Of course, it will not become 0, it will become a very small value. So once you become a very small value, this term becomes 0, and you will get only a nu 0 value. That is why if you take this single crystals of this gypsum, that is nothing but calcium sulfate H2O, and then keep at an angle of 54.7 degrees, you can get both the alpha and beta, both the protons will give a single peak. In all the other angles, for example, if you reduce the angle to 30 degree, then what happens? Again, it separates. And when it becomes 0 degree, it separates like anything. So this itself shows how the dipole-dipole interaction changes as a function of angle. This is as a function as the bond vector changes, how the dipole-dipole interaction changes. You see a doublet or two peaks which merges to a single peak and again gets separated into two peaks, as can be seen from here. So this is a typical example of calcium sulfate single crystal in which the water molecules are isolated, and these isolated water molecules, there is no inter-water molecular interaction. Only the protons, intra-proton only interaction is taking place. This, if you see any textbook, you can see this, because this is a very common thing in Google also. You can get the most common thing about this solid state NMR pattern. First, in the beginner, what they introduced is the proton NMR of calcium sulfate water. Now what I have told is about the single crystal, but we don't have single crystals always. We always encounter in the laboratory or in other practical cases, we encounter always powder samples. How a powder pattern will look like? In powder pattern, you will get all type of orientations. Orientation starts from 90 degree to 60 degree, 54.7 degree, 35 degree, 30 degree, 35 degree, 0 degree. All sorts of orientations are possible. So what you will get is a collapse, or if you mix all these patterns, then what you get is a powder pattern. You see here, this is nothing but the powder pattern of calcium sulfate disposal. So you sort of all type of orientations are possible. The proton-proton vector have various angles with respect to the applied magnetic field, and you get a pattern like this. And from that pattern, you can always get what is the RDD. RDD is nothing but dipole-dipole coupling. Sorry, in this case, I have not written as a subscript. So RDD is nothing but the dipole-dipole interaction between the two interacting protons. And you can get the value of dipole-dipole interactions. Once you get the dipole-dipole interaction, RDD is given here in nothing but this expression. And if you know the constant, fundamental constants, as well as the gamma J and gamma K value, which is reported in literature, you can get the average value of RJK. What is RJK? RJK is nothing but the distance between the J and K nucleus. So average distance you can get, and this can be compared with that of the X-ray diffraction results. So this in the literature, if you give Google now the term Peck doublet, what you get is this only. This is a doublet structure which is known as the Peck doublet, and this is nothing but the Peck doublet obtained from proton NMR of calcium sulfate disposal. So as I mentioned, the strength of the dipole-dipole interaction depends upon many parameters. Like one is the distance, I have told. As the distance increases, the dipole-dipole interaction decreases because it is inversely proportional to the cube of the distance. And another parameter, which I have also mentioned during the first lecture, also in the beginning today, that the gyromagnetic ratio. Carbon is having a very small value of gyromagnetic ratio compared to proton, because among all the nucleus, proton is having the highest gyromagnetic ratio. You see the values here. The RDD values are quite high, 120 kilohertz for proton-proton interaction, one bond coupling. Whereas in the case of proton carbon 13, it is 30 kilohertz. And if the distance is higher, for example, if this proton and carbon 13 is 1 angstrom, the moment you go to proton carbon 13 with 2 angstrom, it further decreases. So you can have an understanding, or you can have a feel how the dipole interaction depends on the distance. So let me summarize the results on the gypsum or calcium sulfate crystal. So gypsum is a hydrated calcium sulfate with composition CaSO4 2H2O. It commonly occurs as a chalky powder. So here we have got CaO8 and SO4 polyhedra. So this is nothing but the information which we get from X-ray crystallography. But X-ray crystallography doesn't say much about the proton. So this information has been obtained, that isolated protons in calcium sulfate, hydrated calcium sulfate, is obtained exclusively from NMR technique. So OH bond length also has been evaluated, and the hydrogen bonds also, because the protons are somewhat different in structure. So that is why we have got two different hydrogen bond lengths, 2.816 and 2.896 angstrom, as well as the OH bond lengths are also quite different. So just for the sake of completion, I thought I will show you calcium sulfate structure also. Calcium sulfate, hydrated calcium sulfate. The water molecules are there inside the layers. You see here, these are the water molecules, H2O molecules here. These are the H2O molecules. They are in between the layers. The layers are formed by CaO8. You see the green color is Ca. 4 are on the surface, 2 above, 2 below. So 4 plus 2 plus 2, 6 plus 8. 6 plus 2, 8. 4 here on this green bonds, oxygen. And 2 above, 4 plus 2, 6, and 2 below, 4 plus 2, 6. It is CaO8 tetrahedra or polyhedra. And then we have SO4 tetrahedra. SO4 tetrahedra is indicated by the yellow color. One oxygen here, one oxygen here, one oxygen here, one oxygen, SO4 tetrahedra. They are corner shaded, and H2O molecules are in between. See here, H2O molecules are in between. So two different types of protons are there. So two different bond lengths are there. OH bond lengths are there, which is confirmed from the NMR studies, 0.962 angstrom and 0.944 angstrom, and in solids actually. Then we have also have different bond length, hydrogen bonds, which is having your hydrogen bonds are also having secondary bond forces, so the distances are also different. 2.816 and 2.896. This information is exclusively obtained from the NMR studies. So each pair of water molecules is well separated from the air. So it's a simplest system which we have, which people have investigated long back. This is a result of 10, 30, 40 years back. So this also we are showing as a function of this one how the NMR signal changes. So this probably we will not discuss at this stage. So another important aspect is the second moment from the NMR. If you from the NMR line shape also, people can simulate from the NMR line shape, what is the geometry around the proton. So how the protons are existing, in what geometry protons are existing. So from the line width is nothing but the delta H. Delta H line width can be used to get information, which information of the internuclear distances between two different types of proton. Using this type of expression, actually this we will not discuss much. because of course recently also many papers are also coming on using this type of formulas to evaluate the distance between the proton and between the two different types of protons. So you can see the line shape changes now. So depending upon the line width, the tetrahedral configuration will have this type of line width, and if it is pairs, we have this one. So this probably we will, and triangles have a different types of line shape, triangular arrangement of protons. So this aspect we will discuss it maybe later, or we may not discuss also in the course. If time permits, we will discuss it at the end of this course. So as I mentioned, dipole-dipole interaction gives good information, provided the system is simple. If you have a powder sample, it is very difficult to get, and multiple nuclei. For example, in some of the aluminosilicates, we have 21 different types of silicon. So if 21 different types of silicon will interact, have 21 different types of dipole-dipole interactions, and all of them will give a very, very broad pattern. And from this broad pattern, very difficult to get any information by recording NMR. So this is the simple systems like calcium sulfate water or hydrated calcium sulfate, it is easy to get this information. But the real systems are quite complicated. So this type of method or this type of simple angle variation and etc. cannot give much information on the bond distances. So sometimes what happens, people deuterate the sample. So what will happen once you deuterate the sample, first of all, the gamma ratio, the gyromagnetic ratio is lower for neutron compared to proton. And also the magnetic moment also less. So as a result of this, you can get the reduced value of dipole-dipole interaction, and probably you can get some more information from the line shapes. And then before going to further, now anyway, I have discussed about the dipole-dipole interaction so far. Now the another major interaction is nothing but the chemical shift interaction or chemical shielding tensor. So as I mentioned, both this dipole-dipole interaction or quadrupole interaction or this chemical shielding or chemical shift tensor and the chemical shielding tensor are same only. They are they are the same meaning. So they are same. They represent same only. Chemical shift tensor is nothing but the chemical shielding tensor. So 3D nature of the electron density around a nucleus is given by this parameter chemical shielding tensor or the chemical shift tensor. So as I mentioned, this also having 9 components. So in principle, in laboratory frame, we have got 9 components. The moment you go to principal axis system, we have got 3 components. So principal axis system is a simplified version of the laboratory. So the sigma, how sigma is related? Normally, if you see the term now, the localized magnetic field, of course, this in the other classes also, in the previous classes also might have been told. So localized magnetic field is nothing but B minus sigma into B0. What is B0? B0 is nothing but the applied magnetic field. What is the magnetic field of the NMR spectrometer? And B localized is nothing but the local magnetic field felt at the nucleus. So that is nothing but B0 minus sigma into B, because sigma signature is different because one is electron and another is nucleus. That is why the negative term comes here. So B0 minus sigma B0, that is the local field. So because of the charge difference only we have this minus. So B0 1 minus sigma into B0 comes. So then the sigma is nothing but the shielding constant, and it is related to chemical shift by this expression. Delta can be seen as minus sigma. So sigma sample is nothing but Lamar frequency, which is nothing but nu 0. Sometimes people say nu Lamar, or sometimes we as nu 0 minus nu sample divided by nu Lamar, which is nothing but the sigma of the sample. So it can also be expressed as delta sample, although I think probably might have told in the previous classes also, but again, just to refresh your memory, delta sample, because delta is equal to minus sigma, na? So sample will come here, the Lamar reference is nothing but the Lamar only will come here, and 10 raised to 6 terms, you know why the 10 raised to 6 term is nothing but this difference is only hertz and this difference is megahertz. So to get a reasonable number, we multiply with the 10 raised to 6. So delta sample is nothing but nu sigma minus nu sample minus 1 minus sigma reference. As you know, sigma reference is very, very small. So we get on all practical purpose, delta sample can be represented as sigma reference minus sigma sample. So I proceed further. So as I mentioned, so in the case of a solution, the electronic environment will be circular, spherical. But in the case of a solid, the electronic environment will be either this type is elongated, is an oblate or a toroid or like a coconut shape. Elongated coconut, not a spherical coconut, it's an elongated coconut. So along the x-axis, along a major axis, or it can be in the other way also, prolate or oblate shape. And this shows a tensor. And the axis principal components are also there. You see the sigma xx, sigma yy, and sigma xl. These are the principal components of the chemical shift tensor. And this is nothing but the x, y, z are nothing but the laboratory coordinate system. And the dotted lines are nothing but the principal coordinate system, principal axis system. And this principal axis system, we have three components. One is xx, yy, and yz. These parameters can be calculated also in the case of the chemical shift tensor. So same case as I have discussed in the case of a dipole-dipole tensor, we have also guessed a diagonal tensor and a non-diagonal tensor. So this sigma xx, sigma yy, sigma z, sometimes people call it sigma 1, sigma 2, sigma 3. So this also can get averaged to get the sigma isotropic value. So this is nothing but the principal axis system, and this is the lab frame. The same analogy you can make with that of the dipole-dipole interactions. This is I have also mentioned how the Hamiltonian for the dipole-dipole interaction will look like. Similarly, this is a typical Hamiltonian for a chemical shift interaction. With this Hamiltonian, from this Hamiltonian, we can derive the sigma value, sigma z, because normally we try with the IZ component. So sigma z is the predominant component of the chemical shift which interact with the operator. So there is a parameter called the sigma isotropic, which is nothing but the 1/3 of the sigma xx, sigma yy plus sigma zz. That is called the isotropic chemical shift or isotropic chemical shift tensor or isotropic chemical shielding, etc. These are all relate to the same parameter only. So sigma zz nothing along the z axis is given by sigma iso plus delta sigma. Delta sigma is what? Delta sigma is nothing but sigma zz minus sigma isotropic. What is sigma zz? Sigma z is nothing but this component. By convention, sigma z is the highest number, and then comes sigma yy, and then comes sigma xx. So sigma xx is the lowest number. That is by IUPAC conversion. Sigma yy is the next number, next highest number, and sigma zz is the highest number. So that is why here we have taken sigma zz minus sigma isotropic. So delta sigma is nothing but the anisotropy parameter, which is nothing but sigma zz minus sigma iso. So any solid state NMR, if you take, after getting the line shape, we get this anisotropy parameter. That explains if the anisotropy is very, very high, we say it's a highly distorted environment. It is not a cubic environment. It is not a symmetric environment. There is no cubic symmetry. And this delta sigma can be correlated with the symmetry of the lattice or the symmetry of the local environment. Higher the delta sigma, less will be the symmetry. And there is also an asymmetric parameter which will be clear to you from the next slides. Asymmetric parameter is nothing but sigma xx minus sigma yy divided by sigma zz minus sigma x. Actually, you take asymmetric parameters expressed. Sometimes people say as minus also. Sometimes we take as a plus also, because sigma x is a smaller number. So sometimes you get minus and sometimes you get plus. I will show you in a typical pattern how you get minus and how you get plus. So these are the typical parameters which we get from the solid state NMR pattern. One is nothing but the chemical shift value or the isotropic chemical shift value, and another is nothing but the sigma values. Sigma z is shown here. Of course, there are methods to calculate sigma 1, sigma 2, sigma 3, etc., which is nothing but sigma xx, sigma yy, and sigma z. Throughout this manuscript, throughout this presentation, I will be either making sigma z or sigma xx or sigma yy or sigma 1 or sigma 2, sigma 3. So all are same only. Instead of 1 you can take as xx, 2 you can take as yy, and 3 you can take as z. Another thing also you may notice here, see, like dipole-dipole interaction, we have also terminology called the 3 cos squared theta minus 1. This angular term is here also, it is there. Of course, other angular terms are also there. But if you see here, the angular terms here is less complicated. The angular term is, because of 2 terms are only there compared to that of dipole-dipole interaction. Sorry, something. Okay. So these are the parameters which you get. So you remember the 3 cos squared theta minus term 1 in this dipole-dipole interaction as well as the chemical shift anisotropy. So what will be the shape of an NMR signal if it is having the chemical shift or the shielding tensor, predominated by shielding tensor? If I have dipole-dipole interaction, I have told. If you have a powder pattern, how does it look like? How a single pattern will look like in the case of calcium sulfate dysprosium system. But calcium sulfate dysprosium system is a simplest system. And in the case of a normal system, there are a lot of interactions are there. We will get a very broad line shape, which we will discuss a little bit later. But if the interaction between the nucleus are dominated by the chemical shift anisotropy or chemical shielding anisotropy, the line shape you get is like this. If you take a static NMR pattern, you will get a something line shape like this. So once you get a line shape like this, one can calculate what will be the sigma. Sigma you know means delta also you know, very easy. Sigma 1, sigma 2, very easy, no need to do any fitting or no any simulation. You can easily find out from the pattern itself what is sigma 1, sigma 2, sigma 3, and you can calculate also the sigma isotropy. So as I mentioned, sigma 1 is same as sigma XX, sigma YY is same as sigma 2. I will not be discussing the bottom pattern. This I will come back with you. So these are the steps through which we arrive at this equation. This 3 cos squared theta minus 1 is this is the final expression. These are the steps involved. Probably steps we will not discuss in this case. Actually, this is a final expression. This final expression is mentioned here. So as a function of theta and phi, how the frequency, chemical shift frequency changes, how the line shape comes, is expressed by this equation. Probably we will not, you need not remember also about any of this equation. Only remember about the line shape. How a line shape looks like if it is a static NMR pattern of solids. A typical line shape we get is like this. So by IUPAC conversion, IUPAC also indicated by recording static sample, you should have sigma 11 should be from this direction we should go. The highest shielding is for sigma 33. Then comes sigma 22, and then comes sigma 11. Sigma 11 is the least shielded parameter, and sigma 22 is the next shielded, and sigma 33 is the most shielded parameter. So sigma 33 is the most negative actually. So delta 11 will be what? Delta 1. If you see here, delta 11 will have the reverse trend actually. Because sigma is nothing but delta, I have mentioned here, minus delta. You see here, now sigma chemical shift delta can be related to minus sigma. Just I am showing one experimental pattern. This has been taken from a literature, Journal of Molecular Structures, sometime back, few years back. This have taken mercury. Why I have taken mercury? Mercury is having a highest number, Z, very high Z value. So with this H11 in mercury NMR, see how much broad it is. You can get your own information. You can get sigma 11, sigma 22. This is something like this, correct? Na? Similar, the pattern is something like this. Here, if you say sigma XX or sigma YY or sigma 11 is equal to sigma 22, if sigma 11 and sigma 22 are same, what happens? We will get a similar line shape. Is it not? If sigma 11 and sigma 22 are same, we will get exactly similar line shape. Here, sigma 11 and sigma 22 are different, but if you take sigma 11 and sigma 22 same, then what we get is a exactly line shape here. So sigma 11 is equal to sigma 22, and this is nothing but sigma 33. So this is a spin half nucleus. In solid state, we get a similar spectrum like this. So you can get the information regarding sigma. So once you get sigma 11 and sigma 22, you can get information how much, what will be the electron density distribution in around mercury. Now, what happens? This is a static pattern. Now, what happens if you rotate also? This is the static pattern we get. Now, if you rotate it at different frequencies, how it will evolve? If you keep a static pattern, as I mentioned here, this is just a typical static pattern in which sigma 11 is different from sigma 22 and sigma 22 is different from sigma 33. The moment you start rotating, the line shape changes. If you do static is like this. Once you go to 100 hertz, you see line width has decreased. Once you go to kilohertz, further small reduction is there. Once you go to 100 kilohertz, the line shape started decreasing. Once you go to megahertz, you see the line shape has decreased like anything. Why this happens? Why? There is a significant reduction in the line shape as you increase the spinning frequency. And this leads to the concept of magic angle spinning. So keeping at a particular angle, then spinning at very high speed. So this is our strategy. Means keep the sample at a particular angle and then rotate at very high speed. So due to this process, what happens? Interactions gets averaged out and you will get significant line layering. And this is what Andrew and Lowe did, and which revolutionized the solid state NMR spectroscopy, and we can get high resolution NMR signal from solid samples. So here we start a very, very important concept called the magic angle spinning NMR. So let me summarize till this part. So what I have discussed is, I have discussed about dipole-dipole interaction, and then I have discussed about chemical shift interaction. Dipole-dipole interactions have complicated angular dependence, but we depends only the two terminologies. One is term A and term B, which are nothing but the secular components, which have also dependence on a 3 cos squared theta minus 1. Because that is why when you go to magic angle, the 3 cos squared theta minus 1 dependence comes into picture, that significantly reduces the dipole-dipole interaction. And then we have also shown the typical line shapes for protons in gypsum or calcium sulfate hydride. Then we discussed about chemical shift anisotropy. So typical chemical shift anisotropy, this is not due to dipole-dipole interaction, because in the lattice, the two mercuries are well separated. So the ones they are well separated, their distance become very large and the dipole-dipole interaction is negligible. So once the dipole-dipole interaction is negligible, the other predominant interaction comes is nothing but the chemical shift interaction, because this is a spin-half nucleus. The moment it is spin-half, it's a spherically symmetric and there is no quadrupolar interaction is existing. So this will lead to only the chemical shift interactions. There's a purely a chemical shift anisotropy, and that is very clearly seen in this line shape. And from this line shape, we can get information regarding the components of chemical shift anisotropy. So probably I think this magic angle spinning requires some time. Probably maybe in the next class I will discuss. Right. Next class I will discuss this, because then we will again go back to this component of evaluation. These components, this will come back to Mercury NMR again, how to evaluate the sigma 1, sigma 2 components, and how a symmetric tensor will look like. All these parameters we will discuss from this. So two things we are doing. One is nothing but the averaging by rotating at a particular speed, and then we are keeping at a particular angle. So that is why the terminology called magic angle spinning. Keep the sample at the magic angle and spin it at very fast. So what you get is a really solution like NMR line shapes from solids. So this aspect we will discuss in the next class. Please come in the next class also, please attend. Yes. So please. So any doubt, any clarification or any questions, you can stop me also, no need to wait. At any, normally an interaction mode is better rather than going for a monologue. So you are please feel free to stop anytime. I think maybe nobody might have joined. I think one person or any, we can see how many. I think one person has joined. So please feel free to ask any questions. If I don't know, I can refer and then tell you also. There is one simple book is also there. I think we need not go through that, but called solid state NMR, multi-nuclear solid state NMR. So in that first, I think around 1/3, means around 100, first 100 pages, 100 or 120 pages discusses about these line shapes, dipole-dipole interaction, Hamiltonian, how the chemical shift parameter changes as the environment changes, all those things. So please feel free to discuss. Am I going in a speed, sir, or should I reduce the speed? It is okay.
Firstly, because some of these things terms have been already discussed.
Already discussed actually. No need actually to explain.
So next time onwards, na?
Correct.
Little faster. You can write also, use the pen. Na?
probably we getting there will be mostly right actually. I am not very sure.
करके बताओ,
हाँ.
they can feel that कौन किधर बोल रहे हो आप.
Okay. That is one way. Tomorrow I will try. Some sort of a not familiar ना, so थोड़ा सा ये writing.
हाँ, वो उसको जस्ट थोड़ा प्रैक्टिस कर.
बना था right, हाँ.
तो
हो जाएगा.
नहीं है.
It will be smooth है. Okay.
Only thing while writing you don't touch the
अच्छा
screen.
Okay.
Hold the pen that way.
Okay.
That otherwise wherever you are putting na,
Okay.
it senses.
Okay.
And then probably it will change the slide.
Okay. Shall I end the meeting, sir?
Yeah, you end the meeting and you tell that the next class is on Friday. Tell that.
Yes. So please come for the next class. It is on Friday, 3:30 p.m. Please come. We will discuss a very, very interesting topic called magic angle spinning. So far, whatever discussed is only based on some mainly, you can say half theory or half experimental. But now I will go to truly experimental NMR. And I will discuss NMR spectrum from samples, different samples, and what information we can get. This will be very, very interesting. It's much more interesting than these two classes. Because these two classes I was trying to explain the physical aspects of solid state NMR, how the light shape changes, how the other parameters changes. So please come for the next class.
Okay, so
Okay, thank you very much.